they will have 5 speakers. The topic is about sustainable construction. So I think you've heard in the morning as well, the construction industry contributes about 40% to the CO2 emissions of all the industries. And myself, I'm also a project manager for innovation at BCECC, and the scope of my work is also concentrated on sustainable construction. So today we have 5 speakers and 2 chairs. I want to introduce you first also the second chair. So Jason Law, he is the director for service at CBTC. He'll be chairing, let's say, the 2 speakers for architecture, and me then for the experts more for material and the research and development. So the first speaker is Professor Nele de Bailey. She is the director for McNeil Van den Piet Laboratory at UGent University. She has been at UGent for decades, many years, and she has a very large group with more than 20 postdocs and PhD students. And she's an expert in sustainable construction. She developed different types of self-healing concrete. And she has also collaboration with China. She has also, so her former students now became professors in China. So if I may, let's welcome Professor Nele de Bailey for her speech.
Okay, thank you, Lynn, for this nice introduction. Okay, thank you. So indeed at Ghent University I'm chairing the Concrete and Environment Group, and my topic today will be about concrete as an important material in the pursuit towards sustainable infrastructure and circular economy. And actually the 2 main topics in my research group have been over the last years the use of concrete with supplementary cementitious materials. So that includes not only the more common supplementary cementitious materials like blast furnace slag and fly ash. But since those are getting more and more scarce in Belgium, we are also considering other byproducts from industries, like for instance municipal solid waste incineration, bottom ashes, and for instance slag from non-ferrous metallurgy, like copper and lead slag. And then the second important topic is about self-healing. Because, of course, concrete is a material that is quite brittle. It can also already crack at early ages because of the fact that if the cement is reacting with water, the volume is decreasing, so you have autogenous shrinkage, drying shrinkage, which can already lead to cracking at younger age. And these cracks, although they do not really impair the structural stability, they may impair the longer-term durability. So self-healing concrete is aimed at healing these cracks in an autonomous way without human intervention, so no external repair is needed. So these are the main topics, the main 2 large topics, but I was asked by Lynn to concentrate now on projects we have in collaboration with China. Of course, they also fit into those 2 topics, but I will go more in detail for those 2. So actually I will focus on 3 different ones. So the first one is actually a bilateral project which was financed by here in Flanders the FWO and in China by the National Science Foundation of China. And at the Chinese side we have the Chinese Building Materials Academy involved with the colleagues mentioned over there, and several PhD students have been involved in their lab to work on this topic of carbonation of concrete at different carbon dioxide concentrations and also in combination with mechanical load. And at Ghent University we have actually also a Chinese PhD student, Julian Liu, who's working on this topic, and he actually just submitted his PhD to be defended soon. Okay. So the problem, of course, is here that we are looking at concrete, like I said, with different supplementary cementitious materials. And in normal Portland cement concrete, you have quite some buffer because it has a high calcium hydroxide concentration. So when carbon dioxide is entering into the concrete, it reacts with this calcium hydroxide, forming calcium carbonate. But since there is a lot of calcium hydroxide, this ingress, this carbonation process is quite slow. However, if you have pozzolanic materials that react with this Portlandite to form new binders, well, this is positive, of course. That's why we can use them as alternative binders. But on the other hand, it has the downside that you lower the buffering capacity and that carbonation of the concrete can go faster. And I think since this is a session about construction, maybe you know that when the concrete is carbonating, it's not bad for the concrete itself, but when the carbonated zone is reaching the steel reinforcement, it can start to corrode. And that is then one of the most important problems of concrete degradation. Now, generally, we study this carbonation in the lab, and of course there we want to have results faster. So what we do is use carbonation chambers with a higher carbon dioxide concentration. And here in Europe, generally we test at 1% carbon dioxide or 2% if we follow the FIB model code, whereas atmospheric concentration is around 0.04. But in China they have a different standard and they test at 20% CO2. So we wanted to see the effect of the concentration during accelerated testing on the results. And in addition, look at other parameters like concrete composition, age, carbonation time, and so on. And then also, since in a real structure, concrete is mostly under load, we also wanted to investigate the effect of the load on the carbonation rate. So some results of what this PhD student has been doing. For instance, he has been analyzing the mineralogy of the products present in concrete with different percentages, for instance, of blast furnace slag in the normal Portland cement concrete, and then with 50 or 70% of the Portland cement replaced by blast furnace slag. And then he analyzed what is happening if you carbonate under natural conditions or at 1 or 2% carbon dioxide for these different compositions. And for instance, one thing that you can then see is, of course, the Portlandite, the calcium hydroxide, is transformed into various types of calcium carbonate, but this may be different ones depending on, for instance, the carbon dioxide concentration. For instance, at natural conditions here you have a little bit of calcite and much more vaterite, which are two polymorphs of calcium carbonate, but if you increase the level, then this combination, this proportion is changing. So the percentage of carbon dioxide in the accelerated tests will have an effect, for instance, on the polymorphs, also a little bit on the amounts formed, and so on. He also looked at the densification, and especially when you look at natural versus accelerated carbonation, with accelerated carbonation you see more densification of the concrete itself. So this can be studied, for instance, with scanning electron microscopy. Then, like I said, he also tested what is the effect of load. So imagine that concrete in a structure is in a column or a beam under compressive loading. What actually is happening then is that if the load is not too high, you actually compress the pore structure so it becomes less porous. So the CO2 will enter slower, but then micro cracks start forming if you increase the load, and of course the cracks will increase the ingress of CO2. And we wanted to test this with developed equipment to keep the concrete under a constant load with some spring washers and so on. But since concrete is a material that also undergoes creep deformations over time, the easiest was to use creep frames with a pressure vessel to keep the load always constant on this column of stacked prisms. And then you see indeed that carbonation depth, depending on the load level, is decreasing. And then after a certain load level, here being 50% of the failure load, it increases again. And this is quite different, again, depending on the concrete composition, without or with different amounts of blast furnace slag. So this was also studied, for instance, with digital image correlation, where you can see when you increase the load that really micro cracks start forming before you have failure. And the pore densification could also be shown by, for instance, mercury intrusion porosimetry. You see compression of the pore structure under this compressive load. He also modeled this with thermodynamic modeling, looking at how all the different phase assemblages were changing in the portlandite being used, and then the pH gradually decreasing, and that's actually why reinforcement corrosion is starting. And again, this will be different depending on your binder system. But I will not spend too much time because I think I have 15 minutes, so I want to say also something about the other two projects. So this is Jinbing Yang. He's actually a joint PhD student between Tongji University and Ghent University. And he's working with CSE scholarship, spending 2 years at each host institute. And he's working on the use of alkali-activated systems and trying to mitigate shrinkage effects by introducing superabsorbent polymers, which is like a material that you find in baby diapers. These are polymers that can absorb huge amounts of fluids, and they release the fluid again when the concrete is shrinking, hence mitigating the shrinking effect. And later they can also supply more water if the concrete would crack to introduce self-sealing and self-healing. So actually, he did various studies. You saw the 4 topics he is working on. So for instance, he used nuclear magnetic resonance studies to model this absorption-release behavior of the superabsorbent polymers in concrete. And for instance, again, for different compositions with also alkali-activated materials, he saw how with this hump, this is actually the T2 relaxation time, and this hump is showing the water in the superabsorbent polymers and how it is decreasing over time, since it is released to the concrete at the moment it is needed, because otherwise self-desiccation and shrinkage cracking could occur. Oh, that was too fast. He's also looking at those superabsorbent polymers, really measuring this shrinkage effect. So you see over time, indeed, at young age, concrete is shrinking a lot. And if you add different amounts of superabsorbent polymers, 0.1, 3 or 0.5% versus the cement weight, the shrinkage can be mitigated. And he compared this also to expensive agents like gypsum and magnesium oxide. And the combination of, for instance, magnesium oxide and superabsorbent polymers led to the biggest mitigation of the shrinkage effects. And he could also, by XRD, explain why there was this combination gave a synergetic effect. That was actually because the superabsorbent polymers, they stimulated the action of the magnesium oxide. Plastic shrinkage cracking could also be mitigated by superabsorbent polymers. I think only half of the slide is on the screen. But anyway, like for instance, with this alkali-activated material by sodium hydroxide, you can see plastic shrinkage. That's something that occurs when you have very high evaporation rates over fresh concrete. And there, cracking would occur in a reference sample already after 2 hours. Whereas if you have superabsorbent polymers, no cracks were seen. With other compositions, maybe there were some cracks at lower dosages, but then not anymore at higher dosages of superabsorbent polymer. And this can be also linked to the capillary pressure that is formed in the pores of the concrete. So if the pressures are increasing, then you can have this shrinkage cracking effect, but that occurs normally quite fast and later when you have the superabsorbent polymers. And the pressure breakthrough comes then much later. So that's then a positive effect. He also studied self-healing in different mixes, and for instance in this mix with sodium carbonate activated slag, you can see quite nice self-healing effects. And thus this is a crack formed, and then you have we leave it to heal just in contact with moisture for a while, and then you have really stimulation of precipitation in the crack, so that the crack would be closed and no more aggressive agents can penetrate through the crack. Then finally, Xijiao Zhu was also a CSC student who did her whole PhD in our lab, and she was working on microbial self-healing. That is a topic we have been working on already for quite a while. Actually, one of the first to work on it was Jianwen Wang. She was also a Chinese PhD student, but she worked on an FWO project in our lab, and she's currently professor in Xi'an Chiao-Tong University. So Xijiao Zhu was actually also co-promoted by Jianwen Wang. So she was looking at different bacterial metabolisms, urea hydrolysis and nitrate reduction. So this was one we have been testing already since a long time. So this is the metabolism of those bacteria that produces calcium carbonate in the cracks when the bacteria are activated. So we have been producing already a demonstration plate. This is a plate over a roof pit at the Oosterweelink in Antwerp that was made with mixed urolytic cultures, self-healing bacteria. And Xijiao wanted to combine the urea hydrolysis with the nitrate reduction pathway. And actually in this process of nitrate reduction, also calcium carbonate can be precipitated for self-healing of cracks. But an intermediate here, by going from nitrate to nitrogen gas, is nitrite, which is a well-known chemical corrosion inhibitor. So while the crack is slowly being healed over a couple of weeks, the nitrite will avoid the initiation of reinforcement corrosion. So she has been studying this combined principle, so measuring, for instance, ammonia to show that urea is, ammonia to show that urea is degraded, so this goes quite fast. So in a few days, bacteria are active and are carrying out their metabolism. The nitrate that is reduced and converted into nitrite is also shown to appear together by the same bacteria. However, if you have calcium present as well, then you can see urea hydrolysis is not influenced, is still going as well as ever, but the nitrate reduction will go a bit slower. But the most important thing is that by the combination of the two pathways, there can be more calcium carbonate precipitation formed in the cracks. And then she did also various studies more related to the microbial metabolism to show that really bacteria could get active in such a very alkaline material as concrete. For instance, people in cement chemistry know probably calorimetric tests. Well, with a microcalorimeter, you can also see the heat that is released by germination and growth of bacteria. So she studied that for various concentrations, cell concentrations of bacteria, the germination and the growth with microcalorimetry. And then she embedded the bacteria in superabsorbent polymers to have the combined mechanism and even better self-healing. So that was the procedure to make chitosan-based superabsorbent polymers with the bacteria inside, study how they were swelling at different pH levels, and then also showing in the hydrogels that the bacteria could still grow and be activated. And then to show really that they would be active in concrete, she also did oxygen use measurements. So we had cracked mortar samples in a reservoir with water, and then we had an oxygen sensing film, so we could actually monitor how the bacteria would become active and start to consume oxygen for germination by measuring the oxygen use. So this is the initial, the color is showing the oxygen concentration. So for the reference, without bacteria, nothing happened. It was keeping this same orange color. But then with the bacteria in the crack, they would become active, start to use oxygen, and you can see that over one day the oxygen is getting depleted, showing the activity of the bacteria. Okay, so that was a very short overview. I just want to tell you that next year we will also organize in Ghent a conference on self-healing, multifunctional and advanced repair technologies in cementitious system, and you're all very welcome to submit an abstract or just attend the conference.
Thank you, Nida. So I see there are many question marks on many audience faces. So if there's anything you don't understand or you want to know more, now is the opportunity to ask. And I want to begin with a question, also in continuation with our previous discussions. I think the biggest challenge of having new materials is having the certificates. You developed the self-healing concrete, the chemistry-based. For example, there's already the Penetron. It's commercialized. And then there is a bio-based with bacteria. So I see this not yet commercialized. And with your experience working in Belgium and in collaboration with China, do you see any differences, in commercializing these new materials here versus in China?
Well, I'm not sure because we are not trying to commercialize anything in China, and actually we are basically a research institute, generally not commercializing ourselves. But indeed, it's always when you talk to companies who are interested to bring one of the products on the market, the question is always, what, of course, does it work? But then secondly, what will happen if we want to bring it on the market? Will we still have the BNOR label, for instance, for our concrete? And even in Europe, it might be quite different, because on the concrete day, there was a speaker from the Netherlands, actually from Basilisk, and they are a spin-off, more or less, of Delft University. They are commercializing their own type of bacteria for self-healing, also selling it. I'm sure they're selling it in Japan for construction works. I don't know about China. I think they're also having some contacts there. But anyway, in the Netherlands, for instance, it's no problem about that they would lose their, like some certificate by adding something special. But people in the audience were immediately commenting, like, oh, in Belgium, you could then maybe lose the BNOR logo, and what will happen then? So maybe for private buildings where people don't care that much about having a certain certificate, it's still okay. But that's always, certification is always a problem, and that takes decades to make it come true if you want a certificate for a certain product.
So is there any question from the audience? No? Then we'll continue with another question. So you have already students, your previous students now are professors in China, and they are working on similar fields, let's say in the similar fields, and it's also some self-healing concrete. Do you see maybe sometimes there's competition between the students and yourself, and that exists?
Not really. I think the distance is far enough in order not to have competition. No, there is still collaboration, actually. Like I said, like Janwin, who is now a professor at Xi'an Jiaotong University, we have been co-supervising Xijiao Zhu. So we are still collaborating. Just a few days ago, she also submitted an abstract to our conference, and so she still wants to visit us again and collaborate more. So
okay, so it's only collaboration. Let's say there's no competition. That's very good. Okay, then thank you very much again.
Thank you, Professor Nelly de Belli, for your interesting presentation on one of the fundamental elements of the architecture and construction, the cement. And now I'm proud to introduce our next speaker, Mr. Nicolas Godelet. As the architect who designed the Belgian embassy to China and Beijing, and Nicolas has been focused on the timber architecture, I would say. And now, as also graduated from the UC Louvain, you've been working on the field for, I bet, a lot of years, 20 years. So now, please welcome Nicolas Godelet to introduce his work to the audiences. Thank you.
Thank you very much. Hello everyone， 大家好，我叫葛建，葛建隔壁摊的葛，然后建筑的建，外国名字叫 Nicolas Godelet。I'm a Belgian and I lived 20 years in China, and I'm working on a platform that is called NGLab. It's quite a big platform, and we are working on very different kind of project. And today I will try to speak about places I like very much, speak about the goals of the 21st century, sustainability. I work on sustainability for more than 20 years since I'm a student, and I try to promote a strategy of working on sustainable projects through different aspects and different disciplines. Of course, you heard today construction emission is huge. Materials and need for new materials is we have a huge demand. We know that for many materials we need a high level of energy to produce them, and now we are focusing on very super low energy needs for material production. That's the goal I'm trying to focus on. Sustainability, 可持续, what is it? It's a philosophy, it's a strategy, it's also speaking about techniques, but it's considering time and all the field of the environment. We become our environment. 我们变成环境. We become our environment by what we eat, what we drink, and where we live, how we breathe. And that's why environment study is very important. And for me, sustainability would be defined as all the fields of this environment that gather in your project, any kind of project, technical project, architecture, city project. Architecture and city need to create an echo with all these fields. So as an architect, I cannot work as an architect. I have to work with society, culture, with economy, with the landscape, with the climate. Measurable and unmeasurable data. And that's very different from what you hear a lot. Measurable data are the key points for sustainability. Now it's not true. We have to be more global and work on all the fields of environments. Technologies too. Everything must be considered as a whole. Otherwise, sustainability cannot exist on the long term. Measurable and unmeasurable potentials. Methodology. It's for us, we try to work with all the projects on benefits and take from the environment. You have to give benefits to the environment when you use it. And you have to be protected from this environment that is harsh, but also protected. And if you do that for all the different aspects of sustainability, you can try to create a certain base for that sustainability. And NGLab is an international platform. It's a small platform with very different people, researchers, crafters, engineers, architects, and we work all together on different projects. So the team, our teams are changing following what we study, and we work on the elements. Elements and materials are a base for us to create new architecture. We work with, sorry for the other part, you can see those. I bet it's like that. But we work with energy as materials, PLA-X, or recycled materials, wood and grass, because I think the 21st century will be the grass century on construction. Now, maybe I wanted to share some experience with you so that we can travel a little bit in Belgium and in China, because China is also my country, where I grew up, and I wanted to share my city. Not all the projects we have done in China, because there are many, but only in Beijing, so we can have a look at a few projects and how maybe it could be sustainable as a project. You know Louvain-la-Neuve, it's important. That's where I studied, and I like this city because it's super green. It's a city where Chinese industries have taken roots, and also because it's focused on people. That is an incredible and very difficult thing to achieve when you create a city. This achievement, I think, is because it's a very late built city, and China has chance to create new cities and to go to this path of people-oriented urban spaces, landscape, to reintroduce landscape in the city, because we have a lot of roads. And Louvain-la-Neuve, for that, I think is a great mix between economic activity, natural potential, and society potential. Especially with our CBTC Center, that is a great collaboration between Belgium and China. We are, between China and Europe, one continent. I heard this morning 2 continents. We are not 2 continents, we are one continent. It's a continuous land between Belgium and China, and we have roots, common roots. From the ancient time, if you compare Phoenician to Tiakuan, it's a very ancient scripture in China, that we could understand each other 3,000 years ago. It's funny, but alphabet is not just a sign, A, B, C. A means Aleph, means cow. It's almost the same as the Niao. And the house is Bet, B, the B letter, seen from above. In China, we don't see it from above, we see it from the side. We have the roof, the earth, the structure, and the roof. Tian, Jia, Deng Deng. Tian. We share common grounds and we share common culture from very ancient times, and we have always exchanged our knowledge between the 2 countries and the 2 areas. That's my house and that's my office. I live in the very center of Beijing, and our office is over there. Beijing has seen a lot of huge changes, and you see that in Beijing it's a very green city, in fact. Most foreigners don't know that, but in the very core of Beijing city, it's full of gardens, very pleasant life. It's a city that's growing to the 6th Ring Road now, 30 kilometers diameter. It's a huge expansion, and Beijing faces a lot of needs, new needs, in terms of energy, transportation, water, and is trying to connect, to be connected and interconnect between Beijing, the sea, and in the land. You see that this huge area is full of agriculture, but we have a big problem, we don't have enough water. So we need to focus on many, many things. People, interactions, circulation, interaction, and business development. Especially difficult in Beijing because it's a very political city, so you have to be... Let's walk through a few projects that you may know that we have done on Beijing, and we are mainly focusing on the center axis of Beijing, that is Chang'an. And I will talk a little bit about sustainability through different aspects. Cultural city. We worked on the National Theatre. It's a very old project from 2005. We did a metallic structure. It changes completely the landscape of architecture and landscape feeling. It is not architecture, it is not landscape, it's both. We used water to cool down all this surrounding area. And we use a high-tech... Is it you, me? Okay. I'm going to be fast, but you see that this high-tech was created in 2002. We didn't do that in Europe at that time. It's a super light structure, a lot of economy in the steel thicknesses, because of the techniques and the programs we use to calculate this building. French Cultural Center, that is talking about culture. This building is another one. The first one you saw was 10 years ago. This one was a few years ago. And we already use the first building in Beijing made with CLT, that is counter-laminated wood. Now we are studying high-rise building made of CLT. So concrete will be used for basements, we have to, steel for connectors, and wood for main structure and wind counterbracing. This kind of very small project is the beginning of bigger projects. Oh, yeah, sorry. So these natural materials is a huge industry that is developing now in China. 15 years ago, you couldn't find any CLT or laminated wood. Now it's we can find a few companies in China that are developing techniques. Also with high-tech introduction of materials in the CLT to increase its resistance. We work a lot with hemp, Anhui, so hemp and lime. That is a really good materials for non-bearing structures, and that can be natural materials, insulator, and thermic regulator, so hygrometry regulator. Beijing is a sports city, and that was the first sports project we participated in. Was the stadium for 2008 with Herzog and de Meuron, and we did steel structure, high-tech welding consultants on this project. It was very difficult. We had too much steel, so we had to take it off, and the roof disappeared, unfortunately, but it was mandatory. We worked on the last Olympic Games that you have seen, and this one took a completely different orientation from 2008, because we used Shougang, that is a steel mill in Beijing. It's a huge steel mill of 10 square kilometers. We renovate this 3 square kilometers. We worked with Chinese Institute, including Tsinghua, and all this site was completely rehabilitated into sports sport area. Sorry. Okay. So you can see the 3 square kilometers. It was a very polluted site. So we worked on Chinese culture and contemporary site, contemporary architecture, on depollution of very heavy pollution or polluted site, and how to recreate a green city into a very dense environment like Beijing. That's the big air jump. All the snow is produced during night time with only ventilators. All the snow melts after it's brought back to the lake, from the lake making snow again. So we didn't use high-tech systems for that, but we had them in backup. And that was a great event that is quite sustainable, because we finished the project in 2019, so all the events that happened on the big air were already giving back the money of the investment. And that's important to be economically viable when you do a project as an architect. It was completely different from 2008. There's a huge change in the vision of Chinese government on these facilities. Garden city is super important. Here you can see the Belgian pavilion. That is a great opportunity between Chinese engineers and Belgian engineers to create a new structure system that is called tensegrity. You can not see that kind of structure very often. It's very complicated to calculate and especially to build. UNESCO pavilion for the 19 Expo is a bamboo structure. Now we can really focus on the association of new material, of biological materials and steel to create very contemporary structure. They are coming this is the Holland Belgian pavilion with edible landscape. So now we change the landscape so that we try to push cities to create landscapes that you can eat, not just see. And that changes a little bit the data, because you don't choose the same trees, you don't choose the same vegetables. This building is also made of CLT and earth bricks. So these bricks are earth, compressed earth. They are super resistant in compression, and they are not cooked, so no energy is needed for these bricks. You can imagine that to cook a brick you need 1,000 to 200 to 300 degrees. For this one you don't need it. And it's a big game changer in brick production. Representation city, that's the Belgian embassy that will emerge next year. Wood structure, first office building made of wood in Beijing, and all the materials on the base are the residues recycled residues from the other embassy from the 70s, from the 60s, 70s. So we recycle all this material to make the new one. And Belgian government took that risk to give us the project with that idea. Thank you to them. You see that concrete can be recycled in many, many ways. French embassy, I will not talk too much about. I need to control time. 1 minute. All right. Our clients, of course, were the first leaders in energy production in 2005, 2006. We had Veolia Water, even PepsiCo, EDF, to the Blue Core projects is cooling production. Cedar and Tetra Pak, these companies put the first path on technology use to lower energy needs in industry building and office building. We needed them. Otherwise, other investors would not invest in these subjects. Transportation, super important. Beijing is now developing a whole 30 kilometers of bike lanes. We did 6 kilometers of them, built in 6 months, everything prefabricated. The speed is incredible. You cannot do that anywhere else. It's in the north of Beijing. Everything is Alstom, new kind of battery, new kind of transportation and tramways. The Chang'an Bridge that just finished 3 years ago. It's a landscape. We do structure as landscapes, and it changed a little bit the data, because when you do a bridge like that, and it's economy, it's driving economy, because it's a symbolic building, and at that point, we need to invest in operation like this, in big projects. But this project have to bring new values to any site. It's not because it's a bridge that it cannot drive an economic environment. We use Katia to this is also Dassault project. It's the first time that Dassault Katia program is used for bridges. First time used in China on that bridge. And we could save thousands and thousands of tons of steel, because we could calculate all the steel plates, all the elements. Nothing is calculated separately. I will go now to the last one, and I will thank you all for your attention. Shokong, I think, for me, it's an 8 years work. It's a huge work to save all these facilities that have value, historical value. It's not because it's industrial that has no value, it has huge value. And economically speaking, this city is becoming the welcoming city for the Olympics. It's the new image of the new China that is saving heritage and bring super low energy level on all the buildings of the site. 10 square kilometers of new city, green cities. This building is very comfy. Cooling towers. Have you seen cooling tower renovated? No, never. We imploded. Now we can reuse them. Art gallery, wedding room, hotel facility, office buildings, etc. So we saw today an echo to the site. We saw that project should be integrated to culture and an environment to save energy. Low energy and carbon are coming from material, but first from design. Technology is not going to save architects from their duty to save energy. Smart, because it has to be linked with control also. Transversal skills, because specialists cannot talk to each other. And it always lead to unsustainable projects. We need specialists, we need generalists that can let all specialists work together. Flexible cycles, high-tech optimized. And I say optimized. So let's see now how Belgium and China can work together again. And thank you for your attention. Sorry for the delay.
I have some questions maybe from the audiences. Thank you for your interest in the brilliant works all over the world, especially in China. And any questions from the audiences to Mr. Godolet about his practices? This lady, please.
I have a question. All these projects, they seem to be like sort of government-driven or
Public
projects, yes. Do you see also in smaller constructions, like for normal people, random houses?
Yeah.
This do you see this trend that people are demanding actually?
You're right, because now in China it's difficult to work with private clients because the land is not private owned. But for some cases it happens, for developers it happens. In Belgium and Europe it happens a lot. So all our architects in Europe, especially Holland, Belgium and France, they are facing a lot of this kind of private intention. People now for these 6 to 8 months asked us autonomous houses. Completely autonomous houses. Private people, they don't want to have any electric facture, energy, so zero energy, and also water treatment for grey water. New kind of dry toilets, comfy, not smelling. So we need to create with companies new kind of dry toilets. Of course, electrical powered. Generator as a backup, and also water heating for the whole system. So now houses, especially in Europe, more than in China, are going to the total independence from a grid with comfort. That was difficult before, I think. Yeah.
Thank you.
Next one.
Yes. Thank you for the presentation. It's interesting. In your last slide, you mentioned smart and optimized digitalization. So I would love to know what has been implemented in terms of process or tools when it comes to digitalization. Is it BIM or smart building or stuff like that?
Yes, of course. BIM for years or so it's existing, but now we are going behind BIM design. Of course, we design everything in 3D, all the systems, all the electrical wires, but now we can control a building and listen to a building. And not only a building, but also the bridge. The big bridge you have seen that was made with Katja Dassault program. Now we listen to all the movements of the buildings, how the foundation are reacting, how the vibration are coming on the platform, but also on the cables, and we can understand exactly how a building or a bridge react to this environment. In terms of energy, it acts also in architecture, but on bridges, it's first. You listen to the structure, and you try
Orchestra.
to the orchestra. Yeah.
Finished? The previous lady finished?
Yeah, I just had a question. So, do you integrate the data related to environmental impact, for example, in the BIM process, or like it's kind of two different processes?
No,
digitization inside, and then you have sustainability.
First, climate, everything that comes first, before any project, before any talk about architecture, is about climates and orientations, land, nature, water percolation, local environment, shadow, that is super important in city environment, for example, and then we try to mix that environment and make an echo to the program. But if you don't do that, of course it's difficult. And you saw in all these projects, they are not all 100% sustainable, I think, because we cannot reach always that goal fully at the level we would like with all the projects. But indeed, it has to be implemented at the very beginning. Otherwise, it's too late. Too late. At the end, it's just for fun. It's just for the green certificate, and that's a bit too bad. Just bad.
Please.
下午好，葛健。
你好。
Thank you very much for a very interesting presentation. I have known your name for 5 or 6 years after you built the very famous bridge in Beijing. My question is that if I heard correctly, you said that the 21st century is the century of glass, right?
Grass.
Yes.
草。
grass.
草。
Okay.
木头。
木头。
我觉得就是这个设计呢，会用更多的自然材料，就是自然材料会替代很多可能混凝土或者其他材料，它就更结构。We need to focus on how to combine 20th century technologies, but with new 21st century technologies. Architecture from the 21st century will have to be different from the 20th century. We are now at the edge, changing slowly by using very precisely concrete, steel at the right place at the right moment. But we are facing a new era for architecture. 谢谢。
Thank you, Mr. Godelet, for your inspiring presentations and answers to questions from the audiences. Thank you for your practice.
Thank
you
you very much.
Must be busy in China. Finish all these projects. So, next we would like to introduce you through the internet, Mr. Ding Wei, which is our landscape architect practicing in Beijing. Graduated from the Tsinghua University, Mr. Ding Wei has more than 20 years of experience practicing landscape architectures all over China. And now please welcome Mr. Ding Wei to bring you a short speak about the practice and discussions of green design method for low carbon parks. Good evening, Mr. Ding Wei. Would you like to say hello to the audiences? Hello.
Hello.
Can I say hello to our audiences in Brussels?
听得到声音吗？
Okay.
你好，听得到声音吗？主持人好，各位与会专家好，很感谢世界绿色设计组织的邀请，能够有幸参与此次中比科技交流研讨会。我是中城规划景观生态研究所的所长丁伟。我今天和大家交流的主题呢是低碳公园的绿色设计方法实践与探讨。 在汇报具体内容之前呢，我问大家一个问题：绿色的公园一定是绿色的吗？之所以问这个问题呢，因为公园设计与建造呢，实际上是我和我的团队现在最主要的工作之一。因为我们在工作当中呢，时常会问到公园的设计与建造什么样是最好的，什么样是能够符合周边居民需求的，什么样的公园又符合现时代意义的。
当然了，这个问题的回答是否定的，因为绿色的定义呢，实际上是具有多层含义的。而对于公园呢，对于绿色，我认为呢，在现时代意义当中，首先就需要问一下，这公园是否是生态的，是否是具有可持续性的。我们国家现在各个行业，然后各个不同的人群都有一个共同的奋斗目标，那就是双碳目标。双碳呢，就是碳达峰、碳中和，当然呢还有减碳、替碳、汇碳、固碳等多种不同的词汇。对于这些词汇呢，我就不一一介绍了。对于这个目标，不仅是包含了我们中国国家的战略问题，同时呢，也是关系到我们每个人的生活，与生活是息息相关的。而谈到这个目标呢，我们的公园设计与建造，除了设计出具有多种不同的绿色空间，种植不同的植物、树、青草、花卉等以外，实现低碳和零碳的目标，也是我们最主要的工作任务之一。那怎么去实现这个目标呢？就必须要有一套很完整、严密的方法去进行指引，而我们对这个方法定义为就是绿色设计。什么样的公园是绿色的？怎么样去形成我们自己的绿色方法、绿色设计方法？公园的建造呢，我认为呢，必须要以全生命周期的视角去审视。而在这个过程当中，我们需要有2点必须关注。第一个呢是要素，第二个是过程。要素呢是物质层面的事情，过程呢是时间的维度。要素物质呢，实际上就是讲求公园在材料的选择、植物的运用、周边自然情况的一些考量。而过程呢，我们必须考量就是在我们设计之初、施工过程之中以及维护运营过程然后在这当中，我们都需要问一下材料的运用是不是绿色低碳的，然后呢，在设计、施工、维护过程如何又去做到绿色低碳。然后回到我们实际项目当中，我和我的团队呢，在全国开展了非常多的项目，其中比如说在浙江丽水，我们正在进行的有10几个项目，而其中呢有4个公园性质的项目。而在这些项目当中，无一例外的甲方都提出了绿色、低碳与生态的目标和诉求。另外呢，我们在重庆、湖北、江西、内蒙也都有相应的项目正在开展和进行当中，甲方也都提出了相应的诉求。所以说，对于这种低碳和生态绿色的目标呢，我们不得不予以重点考量。那我挑出了2个项目，然后和大家进行分享。也希望通过这2个项目呢，来总结出我们自己的一个绿色设计方法，和大家进行交流与探讨。第一个呢，就是重庆茶园大道的生态修复项目；第二个呢，是丽水中央公园规划设计项目。重庆茶园大道生态修复项目呢，总体来说，总体面积有46公顷左右，由多个地块组合而成。因为时间的关系，我没法一一和大家进行介绍，我选择了工业园地块和大家进行分享。工业园地块呢，最初的样子呢，实际上就是一片菜地，同时呢，局部有建筑垃圾回填区。可以看得出，其实绿色很多，但是呢，人并不能进入和使用。而且呢，里面的由于建筑垃圾的填埋呢，也造成了很多的污染。因此呢，我们也希望通过我们的生态修复，使这块场地改造成为具有生态价值的一块场地，同时又能够满足周边居民休闲生活的一个公共场所。我们怎么做呢？首先，第一点是地形的梳理、地形的塑造。 我们呢坚持保留现有的地形地貌，因为最初呢，甲方和施工方是想把我们场地内的一个低洼的雨水低洼的一个地势进行填平，然后这样的话就其实后期的施工难度会减少。但是呢，我们设计的运营呢拒绝，因为如果能够保留这块低洼地势呢，可以使我们整个场地能形成丰富的竖向变化效果，景观效果也会起到非常极大的丰富的作用。另外一点呢，就是我们可以顺应地形来进行设计，这样可以减少土方的外运，也减少土方的分家，可以实现场地的土方平衡。这样的话，从一定意义上来说，可以减少施工方外运土方车辆的碳排放问题。第二个呢，就是海绵设施的运用。我们在整个园区当中呢，增加了雨水收集系统，同时呢，采用了透水的铺装材料。这样的话，就是可以充分的利用雨水，然后这样一部分雨水呢可以反哺地下水，另外一部分呢雨水呢可以进入到我们雨水收集，也就是海绵设施的蓄水池然后通过沉淀净化之后呢，我们可以把这部分水呢又运用到绿化浇灌之中。这样的话，从而可以减少公园的后期维护成本，尽可能的使公园自生长、自循环。另外一点呢，就是植物的栽植。我们在整个项目当中呢，也要求，在施工当中，我们要求施工方尽可能选择当地的苗圃。第二个呢，我们在设计之初呢，也尽可能选择乡土树种，还有一种高惠碳式样植物以及抗污染植物品种。通过这些植物的选择呢，我们可以提高植物的成活率，提高植物的固碳效应。另外一点呢，就是让施工方选择当地苗圃呢，也可以减少外地植物运输过程中我们汽车的一些碳排放量，这样的话也可以进一步的降碳。另外一点呢，就是智慧设施的运用。我们在整个园区当中呢，运用了很多的智慧座椅、智慧灯杆、智慧管理系统，而通过这些新能源、新技术的运用呢，可以进一步的减少地下管网的铺设，有效的减少对能源的消耗。这张图片呢，就是我们在园区当中的智慧座椅的照片，上面呢是采用的是光伏板然后可以由光转为电，然后旁边呢就是可以无线充电，为手机无线充电。设施的布置呢，也为周边的居民提供了很绝佳的休闲交流使用的场所。而这个呢，就是我们通过设计建造之后的一个效果。这个地方就是最初就是我们的建筑垃圾的填埋区建造完之后呢，这块区域也成为了整个园区最受民众欢迎的一个区域。现在呢，人流量也非常的多，也非常受欢迎。第二个案例呢，就是浙江的丽水中央公园的规划设计项目。这个项目呢，实际上最初整个场地之内有着绝佳的自然资源，因为通过这些照片我们可以看得出，就是有谷、水、林、引、路等多种非常值得利用的现状资源。我们也是希望呢，就是因地就市，能够借助于这些资源呢，打造我们浙江山水城市当中的一个溪谷森林，这个也是我们建造的一个目标。我们怎么去做呢？首先第一点就是离水策略，我们结合现有的现状水系，然后呢对现状水系第一步呢进行修整，然后把硬质的驳岸进行软质化处理、自然化处理，使它融入周边的自然。另外就是梳理毛细水网，使它进一步的扩大，然后呢成为我们的水系的一部分。第三步呢就是内部进行连通，另外呢就是把我们内部的水系和外部进行连通，这样就内外相互进行衔接，成为一个系统，使我们整个水系能够形成一个自循环的系统，这样呢也能够自净，能够起到自我净化的作用。这样做完之后呢，就可以在我们整个园区当中形成 打造出具有叠水、小瀑布、溪流、湿地等多种不同风貌的特色水域。而这种不同的特色水域呢，又能够为不同的水生动植物创造良好的生境和生存环境。第二点呢，就是地形策略。这个地形策略呢，实际上是和重庆茶园大道的策略方式是一致的，就是尽可能实现场地内的土邦平衡，局部挖方、局部填方，然后两者进行平衡。第三点呢，就是森林营造策略，这一点呢至关重要。因为我们通过研究和分析之后呢，发现生长中的森林比已经成熟的自然森林体系碳吸收的量要高50%，而且呢，这部分的碳吸收呢，同样也可以抵消城市居民生活使用能源碳排放的2.5%，而这部分数据是非常可观的。因此呢，我们非常重视森林营造这一块。我们怎么做呢？主要有3点。第一点呢，就是近自然的经营。我们整个场地内呢有很多的苗圃而苗圃呢都是比较单一的植物，我们呢会局部增加多个品种的植物与其相配合，这样的话就是可以仿造自然林，从而形成比较稳定的生态系统。这样的话，再借助于自然和时间的力量进行发育与更新。第二点呢，就是速生与慢生相结合。这个原则呢，其实主要考虑到了我们公园近期与远期的一个效果，因为我们公园建设之后呢，都要为民众使用，这样呢就必须要保证公园近期和远期都要有景可看、有景可观。所以说，我们这里头呢会选择了异林树种的搭配种植，同时呢考虑到了速生与慢生树种的相搭配。第三点呢，就是我们打造一种近自然群落。我们选择树形相近、生态习性相似的一些树种，这样可以保证我们群落风貌的自然纯粹、迹象变化的颜色的统一。比如说杉树科，我们选择了水杉、池杉和落羽杉相搭配，来形成一种非常纯粹的自然景观。另外呢，就是生境的营造。我们呢在整个园区当中呢，会采用各种不同的植物环境营造，来满足鸟类、鱼类、昆虫等不同的动物栖息的环境。这样的话，就是可以同时呢又选择各种不同的乡土的食源性植物为鸟类为各种动物昆虫提供1年4季的食物的来源，这样吸引不同的鸟类动物，使我们的森林活起来。再是我们林相的策略。这张图呢实际上是我们公园的一个剖面图，从这张剖面图上可以看出，就是就这一个剖面呢，可以有多种不同的植物的迹象。你比如说有开花的，有常绿阔叶的林带，还有湿地的色叶林带、落叶的阔叶林带以及针阔混交林带，这样就形成不同的迹象和色彩变化。另外还有一点呢，就是非常重要，就是融入自然的道路策略。因为不管我们在公园当中行走，还是我们休息、停留，都需要铺装，都需要广场，而这些呢，势必的话就需要进行硬化处理。但是呢，我们在这个公园的设计当中采取了另外一种方式去处理，就是依据我们现有的田埂、原路和土路来进行布置，把它系统化处理，自然的形成了我们整个园区的交通系统。而我们整个园区当中，除了自行车道以外，其他铺装和原路呢，都是以砂石路、石板路和木板路为主。这些材料呢，都能够很好的融入自然，同时呢，又能够提高铺装的透水率，增加我们雨水反哺自然的一种效益。另外呢，也可以减少后期铺装更新维护的次数，减少成本。另外呢，再是功能场地的策略。前面说到，我们整个公园呢都是处于森林之中，就是想打造营造森林的一种效果。我们所以说所有的功能场地都是处于林下空间进行布置，而这种林下空间呢，我们采用的是一种低干扰、低影响的活动场地，而服务于周边的居民生活，同时呢又能够满足不同年龄层的使用需求。另外呢，再是智慧策略。 因为既然是在森林之中，肯定是有密林，而密林呢，必须要保证人在林中行走的安全性。怎么去做呢？我们就可以借助于我们智慧设施、智慧系统、智慧平台去运用，然后保证人在林中骑车、运动、休闲、散步的安全性，同时又另外一方面也可以保证我们森林的安全，防止森林火灾的出现，以及同时呢，也可以对整个公园的垃圾进行管理等等。这个呢，就是我们想最后实施出来的一些效果。这个是我们自己手绘的一些效果图。我们希望整个森林都是处于密林之中，有溪流，有草地，有花卉还有开阔的水面。在林中呢，有能够满足人临时停留休息的地方，还有比较优美的湿地景观。同时局部呢，还有在林下举办一些小型的聚会活动，还有小剧场。借助于我们市政道路桥下的阴影空间，我们可以种植一些蕨类，或者是蕨类，或者是一些苔藓类的专类园，提高我们整个公园的丰富性。那通过以上案例呢，我们进行一定的总结。什么样才是公园的绿色设计呢？我认为呢，是以主动降碳固碳为目标，以公园形成的全生命周期，利用生态设计、智慧手段、低碳施工与维护的方式，来满足城市居民对公园绿色功能的使用需求。这个呢，我认为就是公园的绿色设计。通过总结呢，绿色设计方法呢，有4个非常关键。第一点呢，就是生态设计。生态设计呢，我认为是减碳固碳最为主要的一个方面，而这其中呢，涉及到海绵设施、乡土植物、森林营造、多样生境、绿色建筑各个方面。第二点呢，就是智慧手段。智慧手段呢，我们是希望呢，通过网络化、智能化、数字化的一些规划设计、管理方式去管理整个园区，在园区之中呢，布置各种不同的智慧设施，而这一点呢，实际上是公园减碳非常有力的一个补充。第3点呢，是低碳施工。低碳施工的过程呢，实际上是我们在公园降碳过程当中最容易忽视的一个地方。比如说我们施工当中材料的运输，然后土方平衡的一些措施，以及施工措施等等等等，这些都值得去细细推敲、细细考量。第4点呢，就是后期维护与运营。这一点呢，也是在公园降碳减碳当中，我认为是最值得挖掘的一个部分。比如说我们园林废弃物的利用，比如说我们就是秋天落叶乔木掉下来的树叶，我们可以回收利用，然后进行反哺自然，增加肥料等等。对于这些，我们都可以降低成本，采用一种生态的手法去运用。另外还有游客的游园的管理、运营的自平衡等等，都是可以节省造价、降低成本，是采用一种生态的手法去处理。另外还有一点就是非常关键，就是标准的制定。前面呢讲的是我们通过项目，然后总结出来的我们自己的一些绿色设计方法的一些总结。这一点呢，我认为呢，如果说要把这个事情做到极致，我认为标准的制定至关重要。然而我们现在团队呢正在和其他绿协和各个公司团队呢正在编制双碳智慧园区建筑电气设计标准，而这个呢标准呢实际上就是在我们规划园区之内，采用一种智慧的手法去实现双碳的目标。这个标准呢将在明年3到4月份的时候编制完成。而同时呢，我们也正在与世界绿色设计组织筹划制定绿色设计公园的一个标准。我们也希望这个标准呢尽快的制定出来，能够指导我们的设计公园的一些工作。同时呢，我们也会遇到一些问题与挑战，有2点。第一呢，就是如何从展示性向真实性转变。因为我们现在实际上 全国呢有很多叫做低碳的公园，但是呢，它真的是低碳公园吗？可能大部分展示意义高于真实性。所以说，我认为我是希望呢，通过我们绿色设计以及低碳方式的一些运用和考量，以及标准的制定呢，真正的做到真实的低碳公园。第二个呢，就是如何平衡利润收入和低碳目标建造的关系。因为低碳目标、低碳的方式呢，往往会采用很多生态的方式、生态的材料，而这些呢，其实会降低各个方面的一些利润收入。而对于这些呢，我是希望后面呢我们的设计也会重点予以关注，进行考量。这个也是我们需要处理的非常重要的一个问题。如果这一点处理不好呢，也可能会影响到我们公园的建设。最后呢，我用重庆茶园大道的当时我们去拍的一张照片收尾。我的汇报呢到此结束。谢谢。
好，谢谢丁所长。Thank you, Mr. Ding Wei. So, Mr. Ding is online. If there's a question from the audience, you can ask now. No, all clear. It's very comprehensive. Okay, in that case, 丁所长，谢谢。那这边没有问题。So we'll go to the next speaker, which is Mr. A.F. Kamerling. Forgive me, my French is not so good. So Mr. A.F. is a mechanical engineer. He graduated from École Polytechnique de Louvain in 1998. He has over 20 years of experience in international business development in different sectors. And he joined FEBOSEM a few years ago. He has also collaboration with BCECC. And he's working on a roadmap 2050 for cement and concrete. So welcome.
Thank you. I'll let you arrange that. Okay, so let's start. And you hear me? Right. And first, I'd like to start with the message that I would like you to recall from this speech. So the take-home message. So first of all, what I would like you to remember is that there is a transition towards climate-neutral construction, which is ongoing, and it is accelerating. It doesn't seem to go fast, sufficiently fast, but it is accelerating. And what is also very interesting, and it is more a European point of view, it has to be supported by policies and level playing field policies. Europe has defined very, let's say, ambitious objectives for 2030 and 2050, and the policies are supporting that. What is also important, so I'll focus on cement and concrete, but actually cement and concrete is just a small part of the construction value chain, and all the players have to play their role in this journey. Concrete will still be around. There are some development of new materials, and it totally makes sense. But concrete has some, let's say, features which are useful, like structural, thermal properties. It is versatile. A lot of things can be done with concrete. A very strong point also is that it is produced locally. With local materials, let's say the granulates, sand, the cement, it's all, let's say, sourced very, very locally. Also, a point which is often not recalled is that concrete is very much integrated in the circular construction and circular economy. And then, also, last point that I would like you to remember, and it was let's say, said also by Nicolas, is that environmental decisions have to be taken based on, let's say, using the right materials at the right place. And there are ways to measure that and to quantify that and to use that to make sure that the best combinations are used. Okay, so agenda first, I'll introduce cement, the federation, our Belgian Cement Federation, then our concrete of our concept of the 5 Cs. How do we plan to achieve climate neutrality of cement, which is quite a challenge. A few examples also along the value chain, and then our vision, circular economy, and also the notion of life cycle analysis to take decisions. Right. Okay, just as a reminder, to produce concrete and cement, making the difference between cement and concrete is not always clear for everyone. We start from a quarry, quarrying the limestone, and then this limestone is crushed, it is introduced into a kiln, or it's, well, there are actually two chemical reactions. The first reaction is called the decarbonization at a temperature around 850 degrees. The calcium carbonate, the limestone, will transform into calcium oxide and CO2. And this is a chemical reaction, and this is unavoidable. You cannot do without this in your process to produce what we call the clinker. The clinker is the active part of cement. And then the first reaction is let's say the process reaction, and then there is a clinker reaction where the calcium oxide will combine with the iron oxide and the silicate to form this famous clinker. A strong point also in Belgium is that most of the fuel that we use here, it's a high energy consumption, of course, as I already said, but we mainly use non-recyclable waste. Not gas, not coal. So it's part of also of the circular economy. Then in the second step, this clinker is milled and combined with other cementitious materials like blast furnace slag or other kinds of materials like calcine clays or other things, which with the objective, let's say, to substitute a part of the clinker, which is the heavy part in cement. Then cement is taken into a facility to produce concrete, and concrete is just a mix of about 10 to 15% cement, water in the same, let's say, in the half of the quantity, and then some granulates and sand. And this forms concrete with a number of combinations of concrete depending on the application. And then it is used either it is let's say as a building materials, building blocks, it's a prefabricated material, or it is poured on site and then it is used, and then the building has its own life. Okay, well, that's just the basic. So in Belgium, small country, we have 3 cement players belonging to large international groups, Heidelberg Materials, Cementi Holding, and Holcim. And you will see most of the cement production is in the Wallonne part of Belgium, the French-speaking part of Belgium, because it's close to the deposits of limestone. The cement plants are always located close to the quarries. Actually, you will just see one plant here for CBR. It's in the port of Ghent, and they're actually using the clinker produced here to mill it in this case, which offers them also the possibility to potentially import clinker from other countries if useful. So I will not spend too much time on that. Let's say to recall the use of concrete in a climate neutral or low carbon society. For buildings, okay, you will need some high quality buildings with a high energy performance. For the infrastructure, this is also key for transport, for canals, water treatment, all the facilities, energy facilities. You will need foundation for wind turbines. You need some concrete at some point, anyhow. And there are also some nice facilities inside cities to improve, let's say, the quality of life in cities. And also something which is also very interesting, cement sector is actually a very small sector globally, and here in Belgium it's a very small one. It's only 1,000 employees. So you see, it's very ridiculous compared to activities in China. But these 1,000 employees are key for the work of 200,000 people working in the construction sector. And this is the same, let's say, standard everywhere. Cement is a small ingredient, But without cement, you don't have concrete. And without concrete, it's very hard to build. Okay, so how do we want, let's say, to put cement and concrete into, let's say, as part of the transformation of the construction mode to go towards climate neutral and circular construction? And we have organized this along what we call the 5 C's. And the first C is called clinker. This is everything which relates to the kiln, all the improvements in the thermal efficiency of the kilns, using other kinds of fuels, and so on. So that's the very technical part, and this is fully the responsibility of the cement sector. The second C is the C of cement. Yeah, the cement itself, which is used to produce the concrete, and here in this case we will, let's say, it relates more to the recipes of cement that can be used to produce concrete. It relates also to the standards. We talked about that also. This is key in this case, introducing standards of cement so that they can be used by the concrete sector to produce materials. And then the third C is concrete. So it's not the responsibility of the cement sector itself, because it's the customers, but through the standardization, of course, concrete is also, let's say, involved in the definition of the new cements. And then there is one which is called construction. Well, we put it as cement producers in one basket, all the actions which are possible at the level of the construction. So the role of the architects, the role of the contractors. So how to design buildings with less concrete, using more, let's say, lighter designs, using concrete at the right place. This is typically what we put in there. Okay, so it's a small bubble for us, but actually it's a big part of the game. And then there is a last one which we like very much. It's called carbonation, recarbonation, and in fact, what it is, it's, let's say, and we talked about it. It's concrete will recarbonate. Okay, it captures CO2 from the atmosphere. Depending on the concentration of CO2, it will increase the process or not. And actually, this is identified as a drawback of concrete, because it may touch, let's say, if the front of carbonation is going too close to the steel reinforcement, you will have a problem. Okay, but at the end of the day, this carbonation on all existing concrete structures worldwide, this becomes significant. And this has been identified by the IPCC in the 6th report of the IPCC, that it is something like, let's say, just to translate it, it's close to 1% of global man-made CO2 emissions. So it becomes significant. So cement, concrete is usually seen, and this is true, as responsible for CO2 emissions and global warming. But there is also a part which is usually forgotten, and we like to remind it. It doesn't change the picture, but we want to remind it. Okay? So, how do we want to, let's say, achieve climate neutrality of cement? So this is the responsibility of the cement producers. Let's imagine that this donut represents 100%, let's say, the climate footprint of cement. In Belgium, in 1990, the average climate footprint of cement was 752 kilograms of CO2 per ton of cement. Okay? Today, we are already 30% lower. So we have achieved a reduction of the carbon intensity of cement. How did we do that? Through energy efficiency. Okay, so that's a classical way for industries to improve their process. Working on the fuel mix. So as I explained, we are using essentially non-recyclable waste, and this decreases, of course, the climate footprint of the cement production. And also working on the cement recipes. In Belgium, we use very much what we call CEM3, which is a cement with a Portland clinker and blast furnace slag, and we use it very much. So, and a way to measure that is what we call the clinker ratio in cement. So the amount, the average amount of clinker which is used per ton of cement. In Belgium, we are at 63%, which is extremely low compared to the standards worldwide. Okay, so how do we get the remaining 70% of the work? Because the first 30%, it was driven, let's say, by the economies actually. It was financial to do it, let's be clear. So 14% of the work will be done through further improvement at the clinker leverage. So that's energy efficiency. So we go further with new techniques. It's not breakthrough innovation in general. It's existing things, but we need to deploy it. Fuels, we can still continue to go further with the core processing, and also what we call alternative raw materials. Some waste from deconstruction can be reused in the cement kiln because they have already been decarbonated, and so it reduces the amount of CO2 which is emitted during the production of clinker. Okay. Further, we will work on the cement part of it and the recipes, new constituents that can be used for cement production, and one particular of attention, that's what we call the calcined clays. There is a famous project which is called the LC3 with the, let's say, from the University of Lausanne, and this goes into the right direction. In Belgium, we absolutely have to do it because today we use a lot of, so as I said, steel blast furnace slags, okay? But this blast furnace slag will disappear someday because the steel sector is also busy with its roadmap and developing new processes like direct reduction of iron ore and things like that. But so they will no longer produce this waste, and so we will not be able to use it for cement production someday. Okay? And also what we call the alternative binders, like the alkali activated materials. These are also directions of research. We are not convinced that it will, let's say, transform all the industry, that 100% of the market will use these materials, but there are some possibilities, and once again we go back to this idea, the right material at the right place for the right application. Okay? And then there is a big thing, which is 35% of the effort, which is through breakthrough technologies. It's a carbon capture for storage or carbon capture for utilization. It is, let's say, a few years ago, I would have said, okay, it's for long term, 2045 something. Today, I can tell you that this will materialize in Europe before 2030. The first plant that will start, the first cement plant that will start with carbon capture and storage, that will be in Norway, and that will be in 2024. It's a plant from Heidelberg. In Belgium, Holcim has introduced a permit for a new plant that should be operational with carbon capture as of 2028. Perhaps they will have some delay, but okay, that's in this range in terms of timing. So it's really short term. There are three main techniques. Three main techniques. First one is what we call oxyfuel. It's using oxygen instead of air for the kiln, which helps concentrating the CO2 in the flue gas. Okay. We have what we call the direct process capture. It's called the LELAC project. The idea with this process is to separate the decarbonization phase, at a lower temperature, with the clinker forming phase in the kiln. So this is also very, very promising. It's an Australian company which is the leader in this technology, and there are already partnerships, pilot plants which are running. So it's very promising. And the one which is the classical technique is called the post-combustion. But so this is really something which will materialize soon. And then, okay, the last thing, that's 6%. That's the, let's say, the consideration of this recarbonation. Okay, it doesn't change really the picture, but we want to take it into account. Okay. And that means also that if it is considered, we can have, let's imagine negative emissions, okay, because carbon capture can go further. But okay, that's how we see how we can produce climate neutral cement in Belgium. It's very similar in Europe. The Global Cement and Concrete Association has also issued a roadmap where they have a different approach. It's the same, let's say, the same ways to achieve it, but they have also considered the total volume and the reduction of the demand of the total volume of concrete and cement in general. Okay, so that's how we want to do it. So just to give some examples of some projects, initiatives at the level along the value chain. At concrete level, the first thing to remind when dealing with sustainability and low carbon footprint is that let's say the durability, the long-term use of the materials is important. If you cast concrete and after 20 years you have a lot of shrinkage and you need to replace it, this doesn't work. So this means that the right rules, the state-of-the-art techniques should be applied to ensure that of the long-term durability of the solutions. And this is why, and this is the basics, in fact. This has been known for years, but we still need to remind it because the knowledge at the contractor side is decreasing everywhere, and so there is, let's say, this effort is still important. When dealing with, let's say, ready-mix concrete, digitalization will certainly help. It's still, even in Belgium, not always highly high-tech. And when dosing cement, but okay, you put some safety, you put a little bit more. Sorry, but just putting 5% more cement, it's okay, it's safe, but it's not good for the footprint at the end of the day. So transport will decarbonize, I think, very easily, because ready-mix concrete is transported on short distances in general, from the plant to the work site, and so electrifying this kind of transport totally makes sense. New concretes also will have some future based on all the chemistry. One is well known, is Solidia. It's an American company who has developed a concrete which will cure with CO2. Okay, so instead of having a positive footprint, it has a negative. Let's say it captures CO2 when it is produced. Of course, it works only if there is an access to a CO2 flow, so it's more relevant for precast materials, of course. And since the pH will be too low, it cannot work with steel reinforcement, of course. But okay, it has some potential applications. Okay. And level of construction, as I said, there are a lot of things to do. We strongly believe that concrete has a very positive impact on the energy efficiency of buildings, in particular through its property of thermal mass. That the fact that it really keeps, when there are heat, let's say peaks of heat, okay, it will stay a bit cool, and so you don't need to have too much cooling in the building, especially let's say with the climate change ongoing, it totally makes sense. In cities also, compared to asphalt, concrete is much lighter, and so it reflects a bit more the light, and so it has a positive effect on the heat island effect. Also, in combination with parks, with green areas in cities, it works very well, and there are very nice, let's say, projects where it's easier to leave space for the greens, for the green areas, thanks to concrete. I know it may sound a bit paradoxical that using concrete will help having some greens, but that's the case in cities. Okay. As I said before, more efficient utilization of building materials, using the right material in the right place. 3D printing with concrete shows some interest. It's still, okay, we're still looking for, let's say, where is it useful actually, but it enables using very, let's say, a smaller amount of material for some special shapes typically. And then you have, and also, as I said, we talked about the BENOR and the standards. This remains something really important. What is also key is that the processes the standard processes have improved. ISO, EN certificates, and the processes have improved for years. So this means also that if a material is certified, has its standards, you don't need to go too much for other safety margins. Okay, everything is well under control. And then, new techniques like design for adaptability, reusing the structures. You see much more, and it was also explained in the project, reusing what is existing as much as possible, giving a second life to a building. This is also now, when new buildings are, let's say, are designed, they are thought of to, okay, it's not just for 30 years, it's not just offices for the next 30 years, but, okay, what after? So I have to design my building to make sure that it can last for 100, 200 years maybe. Okay? This way, it's better. And then the recarbonation. So as I said, carbon can be seen, concrete can be seen as a carbon sink. It's not a total carbon sink, of course, because it emits more. There are more CO2 emissions in producing it than during the capture, but it reduces the combined footprint. And we have, and as I said, there was a, let's say, element from the IPCC report. We made also a study in Europe where we came to the conclusion that it's 23% of the processed CO2 which is reabsorbed during the lifetime of the material. Interestingly, when there is deconstruction, when there is demolition, these concrete aggregates can be easily, let's say, one can improve the recarbonation during, let's say, after the demolition. Circular economy, you have a number of places where concrete can be either reused or recycled, or at the level of cement, or there are a number of steps, I will not detail, but it's different points where I can re-enter the construction value chain. I will not spend too much time on that, but we have developed in Belgium a tool which is enabled to put together the environmental product declarations of each building material, and there are a number of indicators, and this enables for architects to make choices, to make sound choices in the materials and test what is the global footprint, not only climate footprint, the total footprint of all my building materials on the project I'm working on. And this makes it possible to, let's say, to make, to think and choose the right solution. And you may have some building materials with a lower global warming footprint, but a high footprint in terms of let's say, water use, for instance, or use of land. And this has to be taken into account. And this is a reality which depends also on the continent where you work, on the country where you work. So it's not one size fits all. And this is really an important point, that at the design phase, there are some decisions which are taken based on the building materials. So that's it. So that's what we want to achieve. Net zero by 2050, and we still have this date 2050, but I'm pretty sure that we'll go much faster than that. It will not be 2030, but it's somewhere in between. I'm pretty sure that we can achieve that properly. Thank you very much.
Thank you, Evi. Is there any question in the audience?
Yes, you spoke about concrete, and I think there's another very good application of concrete. It's to stabilize the acidity or the basicity of water, or especially rainwater storage. I think it's the only way to store rainwater, to be able to balance the.
Okay. Yes. Yes. It's part indeed, because it's alkaline, and indeed it will. It will help.
Acidity.
Yeah. Absolutely. Yeah. That's part of its nature, and also for water in general, and also like the creating surfaces like impervious surfaces to make sure that water can infiltrate. It's also a set of applications which are seen much more, especially in built environment in cities.
there any way or regulation in Belgium to increase the reuse of materials and be able to promote these materials in construction site for lows or recycled materials, etc.?
It's part, yes, today in Belgium, let's say, there are two things. First, it's let's say, the property owners, the real estate sector is now being pushed by what we call the EU taxonomy. And in the EU taxonomy, there are a number of elements which include let's say, the impact on the use of materials. And so it helps them in scoring also for the BREEAM things, using recycled material, local material, reusing as much as possible the existing structure increases, let's say, the scoring of the material. Also, some municipalities are requesting that. It's part of the permits to, let's say, okay, to no, you may not destroy the building, but you have to let's say, to reuse as much as possible. But so there is no, so it's on a case by case in general. There are no rules are not, let's say, it's not compulsory. It will depend on the specifications in general.
Okay, the lady in the back.
Yeah, that was kind of the same question, like kind of like linked to water as well. Like you just said, it's it could be like net zero by 2050, and you also talk about like the water, how like the building construction could be like net zero, but the water could link the company to not be net zero. That's what you said.
Excuse me, I'm a little bit deaf. So
you just said before about like the net zero by 2050, and you made a link with the water just before. Like before like the end of the presentation, how like the building could be net zero, but the water could increase then the carbonization of the building. That's what you said, right?
Oh no. What I said, so just before the comparison of the footprint of different building materials.
Yes, like what I understood is like by the using of the cement from your company, the footprint could be like less than it used to be, but the water footprints could be higher. And
it depends. So here on the slide, what I did a small exercise and building, let's say, an apartment building, and one was based on a structure based on CLT, and the other one was based on concrete. And based on the information which is available in the environmental product declarations, you see that okay, at the end of the day, it's not, there is no big difference in terms of footprint of the solution, but there is indeed a difference in the different impacts, let's say, on the total footprint. The footprint will add each impact based on a rule which can be discussed, of course, but there are some methods. And then what we saw is that in this case, let's say the concrete-based building was a bit more, let's say, expensive regarding global warming potential, so the carbon footprint, but on other indicators like land use, water use, or others, CLT was more relevant, or let's say, or the pollutants, thanks to the glues, for instance, in this case, and it was a bit higher. And at the end of the day, it's a choice. It's a matter of choice. Everything has an impact, has a footprint. It's a matter of choice. This was also based on, let's say, basic analysis. If, let's say, the next step probably with this kind of analysis, okay, how can I really optimize and combine my concrete for this and some CLT there and another building material, and this I can achieve the best solution, let's say, with an objective in terms of energy efficiency and an objective of, let's say, lowering as much as possible the footprint of my building. This is the way to use it. It's a bit, let's say, we like to make a caricature to show, okay, concrete is better, CLT is better, but it doesn't make sense at the end of the day.
Okay.
Did I understand? Did I answer your question?
Yeah, we're running a bit late, so I think you can discuss later. Also, there's during the coffee break. Also, please discuss afterwards. So, thank you again.
Thank you.
experience in the field of residual valorization. She got her PhD at the Department of Materials Engineering at KU Leuven in 2013 and continued as a postdoc. And now she is the research manager in the Srimat group at KU Leuven. And I met her at also a conference. She works on so renewable materials using waste materials and is very good for fire resistance. So please welcome.
Ladies and gentlemen, thank you very much for having me. And I'll speak a little bit about how to implement or how to use residues as building materials. So I hope I will convince my previous speaker that the alternative materials are maybe not completely at the edge, so that they can be a bigger part of making greener construction. So a little bit of the cement history. So cement as a material was invented in 1824 by accident, actually. Well, sort of. As it happens, a stonemaker mixed a bit of limestone and a bit of clay in his kitchen stove, and then he came up with the first hydraulic cement, which became the world's most used building material. How it is now, almost 200 years later, we're still using it. So it was a good accident. A bit of cement data, we can have a discussion later on, but cement, as you already heard, the cement production is accompanied with large CO2 emissions, and if you think about the large production of cement, being 4.4 gigaton, this come up with the CO2 of about 8% of all anthropogenic CO2 every year is associated with the production of cement. This material by itself is not that much reusable, but okay, there are some recyclable, but there are some options definitely. But I think we can agree that it is using a lot of raw materials, primarily raw materials. So I think we need to change this because we cannot continue like that. Is there a future for cement? If you look at the cement website, then there are new innovations. There are trends to improve the sustainability, strength, application, etc. So I think yes, there is future for cement, and I think it would be a bit silly to say cement should not be part of construction sector. Is it good? Well, to use this material in these quantities, okay, that's a question. I think we should look at alternatives, maybe niche markets for other materials. So what we do is in a Sremat group, which is the group of KU Leuven, focus on sustainable resources. We focus on iron-rich industrial residues, mainly bauxite residue, so residue from aluminum production or copper slags. So if we look at the copper slag as a case study, copper slag looks like so it is like 30 to 60 iron oxide, then is some silica, calcium, alumina, and due to the water quenching, it is above 85% amorphous, which makes it ideal precursor for inorganic polymers binder. Now, what is inorganic polymer? Inorganic polymer is a polymer that is actually it doesn't have any carbon in its structure. That's why I call it inorganic. And it's made by dissolving alumina silicates or iron alumina silicates in alkaline environment. Then there is some gelation, polymerization, and hardening. And like that, we create a binder. So this binder, all this reaction happen at room temperature. So we have very low or much significantly lower CO2 footprint, and we end up with a material that has quite good mechanical properties, and compared to cement or compared to concrete, some superior like fire or chemical resistance. Okay, so how do we actually work with, or how do we create inorganic polymers? We basically take the amorphous precursor, alkaline activator, which can be hydroxide or silicate. We mix it and we end up with inorganic polymer paste, and this paste can be pressed, casted, 3D printed, or foamed. It can be cured at room temperature, it can be cured hydrothermally, so in big autoclave, it can be even fired, depending on the application that you want to use it for. Some case study, because the title said that we go for unique properties, so let's start with the one of high temperature properties and resistance, and fire resistance. So, in my previous slide, I said how inorganic polymer can be made. Now, if you take the mix design and you put, you play with your, with your mix design, then you can end up with a mixture that has different behavior at high temperature. So if you can end up with material that has quite low melting points, where you can maybe use this material as glass ceramic, or you can use it as a glaze, or you can make the mix design in such a way that you end up with pacifier protection boards or even refractory materials. How do we do it? So you take your slag chemistry, additives, alkali activation, and you look at some ratios. There are silica, potassium, alumina, potassium, etc. And you basically make different mix designs, and you look at the crystallization behavior and at the phases assemblaged at high temperature. You want to know what are the melting temperatures of these phases, and then basically you pick the right mix design for your application. What you also do is you go and study a bit of literature. You look at all the possible phases that are in your, possible from your elements, and you pick the phase that you want to, that has the melting temperature that you want, and then you fire your mix design. And you see that, okay, there is always an ideal combination, and you can end up with inorganic polymer that is fire resistant at 1350, and it creates, during this firing, it creates a fire resistant phase that can withstand even higher temperature. This study was done by a colleague of mine, Bjorn van der Sande, who is about to defend his PhD. Then you can also do a bit of like what properties you want. So depending on the properties at the room temperature, you can either go for low or higher strength demand, and then based on that you have some kind of price. Okay. The other part of which I will share with you is the lightweight inorganic polymers. Sorry for the title. Basically, as I said in the beginning of my presentation, you can also create lightweight materials by either introducing the foam, so mechanical activation, mechanical foaming, or by putting aluminium and you can chemically foam your material. And then again, depending on your application, you either create a load-bearing thermal insulating material, such as ketone block or something, sound insulation or sound absorption panels, for instance, for the highways, the panels that are at the highways to absorb the sound, or again, a lightweight fire-resistant panels, for instance, to protect the concrete structure in the tunnels. If you look at the load-bearing and thermal applications, then this is, for instance, these are the graphs for compressive strength, for the density that you can get. And if you look at this region, which is between 1,000 and 1,500 density, this is the region where typically we are interested in when we talk about the load-bearing insulating materials, because here the lambda value is around 0.1 to 0.15. if we look at the sound absorption, as I said, then you can end up with a sandwich panel, which consists of porous inorganic polymer, air gap, and a dense inorganic polymer, and you can have sound absorption almost up to 100% in the region that is. This is the frequencies that are typical for highways, so you can have absorbed the sound. Or you can go for the lightweight porous inorganic polymers, where you see this is the lightweight panel. I think the density is around 1100 before, and you see the thickness of 5 centimeter. After exposing to the firing, we see 2 zones, so it was way too thick because the half of the panel was not intact, and in the front part, which was in contact with the fire, we see the formation again of the phases that are resistant to high temperature, so we are forming these refractory phases. You can also do big scale. Of course, we want to upscale, so we produce this 100 centimeter, but almost like a 1 by 2 meter panel, and then have it tested in Technalia. And then we see that the ISO curve that our panel actually failed after 92 minutes, which is quite good. Or you can even do another test and you will see that actually it will hold the panel structure will hold for more than 4 hours to protect your concrete structure. So it's definitely promising. This work was done by a colleague of mine, Roberto Murillo, and he's going to defend his PhD soon. So, and with this, I would like to thank to Professor Ponticus, who is the supervisor and the head of our group, and to the whole remote group to generate such a great knowledge and such a good work. And yeah, thank you very much for your attention. I would say yes, but I wouldn't see it as an ultimate replacement of a cement. I see these materials more working on a local level. So I think for us it's very important to have materials that are available at the local level, and then they can be also applied at the local level. Because of course you cannot have the same material, or I think it's silly to have the same material developed here and then have all the materials that are available here shipped to another continent or something. So at that point, they should figure out, or people should just figure out and work more locally. And I see it more as because also the quantities are not that large. So again, I see more to use this material for niche applications where we are better than cement, because it would also be silly to replace material that works very well with something that doesn't work that well. So let's have a look at the applications where inorganic polymers are better or can work better than cement, and use them there.
Yeah. Okay, thank you again. So thank you to all the speakers today and the audience for coming. This will be the end of the sustainable construction session. We're on time. So we'll have a coffee break. Then we'll meet again at around 4 o'clock for the roundtable discussion.
Recording stopped.